Hello, good afternoon, everyone. I would like to welcome you all to the second Library Technology Conclave, PreConclave workshop on semantic search, the current frontier of search technology, to be given by Professor Ricardo Baeza Yates. Thank you all for registering and joining us today. Before I introduce you, the speaker, Professor Ricardo Baeza Yates, let me just give you a brief overview of what LTC 2021 is about. Library Technology Conclave 2021 is fifth in the series, started by Informatics India Limited, and every year they conduct this conclave in partnership with different organizations. This year, that is the LTC 2021, is organized by Informatics India in collaboration with National Institute of Advanced Studies, Bangalore, and then Rajiv Gandhi University of Health Sciences, Bangalore, and then the CSIR Fourth Paradigm Research Institute, Bangalore. I am the program chair. I am Shalini Aras. As program chair, I am your host today. We'll take you through the proceedings of today's workshop. Well, about the conference, about the Library Technology Conclave, all of you know that library and technology, these two, have a long history of a strong alliance. Today we are talking about, of course, Professor Baeza Yates will be talking about the semantic search, but I suppose all of you have studied history of classification and cataloging, etc., in your library information science courses, know that the first library catalog or the first library cataloger, Callimachus of the Alexandrian library, was in fact, in a way, you can say, when he built its Pinnacus, the catalog, built the first, probably the semantic search. Because in that catalog, so that's why we consider Callimachus as the first cataloger in the world. Because remember, those days also, the Alexandrian library had about 500,000 papyrus rolls. And he cataloged it, connected the author, and then the summary of it, everything he provided in this, in his catalog. So it dates back the connection between developing a very relevant, findable discovery tool to find resources relevant to one's intent goes back to about 300 BC. And later, we know we have studied in, I'm sure many of you have studied the duodecimal classification system. The relative index of DDC was one of the, I would say, greatest technology of that time, because he could bring together what probably in his talk, Ricardo Baeza will be talking about annotated indexes, annotated to build the semantic search. So in one sense, what I was trying to say here is the alliance between the topic of today, that is semantic search, and then the library and information science professions search for technologies to enable or be a proper bridge between the seeker of information, seeker of knowledge, and then the knowledge itself goes back to millennia. So with this introduction about the conclave, library technology conclave, and the theme of this conclave, the overall theme of the conclave is e-science and digital libraries. And the conclave will actually start, the actual conclave will start from January 27th to 30th. As many of you probably already know, that this is our fifth pre-conclave event. So this fifth pre-conclave event is a workshop, which my dear friend Ricardo Baeza Yates has kindly agreed to give on search technology. And let me give you a very brief introduction. I'm sure many of you, those of you who have taken a course on information retrieval, are familiar with the name Professor Ricardo Baeza Yates, because his book, Modern Information Retrieval, published in 1999, as a co-author is considered not just a bestseller, but a classic in information retrieval. So anyone who has taken a course in my information retrieval would have actually used that as a textbook. But I do not want to fail in my duty to do the formal introduction. So Professor Baeza Yates is currently a research professor at the Northeastern University at Silicon Valley, California. He also heads the data sciences program at this university, and then is part of the Roux Institute of Experiential AI over there. Before this position, he's also involved with actually as a part-time professor in many universities. I will not go into that. I will just mention a few of them. Before this position, he was the co-founder and CTO of search technology, semantic search technology company called the Intent. And then before that, in fact, I guess that's when I met Professor Ricardo when he was part of the Yahoo research. I think we met at one of the digital library conferences. He was heading he was the VP research of Yahoo Labs, and he also set up, founded, and actually ran Yahoo Labs in different parts of the world, from Barcelona to London to other places. Then moved on to the California office. So, and he is also part of the ACM, and he is a fellow of the IEEE, and many of these things I will not go take between you and Ricardo. So I'll just introduce him with this and welcome Professor Ricardo Baeza Yates to this community, to this workshop. A hearty welcome to you, Professor Baeza Yates.
Thank you, Shalini. It's my pleasure to be here.
And then I would also take this opportunity to welcome all our participants who are just joining in now. And we expect the number of participants to be crossing 100. Right now, we have 61 participants because they will slowly trickle in. So they will be joining soon. So we will probably have more than 100 participants in this workshop. So I would like to welcome all our organizing partners, the core committee members. And then with this, I would like to now hand over the platform to Professor Ricardo Baeza Yates. Over to you, Professor.
Yeah, thank you, Shalini. So let me share the presentation.
You can start your presentation, share your, yeah.
So I think to have a better quality sound, I will, while I present, I will take out the video. This will have two parts. So the first part will be mainly in semantic search, and I want to do some exercises with you in the middle. So I am assuming that most of the people is coming from information science, not from computer science. I hope I'm correct. And then the second part will be on query analytics, because if we don't understand the queries, it's very hard to understand what the user wants, and then we cannot do semantic search. So the first part will be an overview, and then the second part I will go more deeper on query analytics, and the main thing will be query intention. So what the user is trying to do, because if you cannot predict what the user is doing, then you cannot give a good experience on semantic search. So this is the part one. I will start with a brief introduction to machine learning, mobile search, and distributed search, because this is the context of what I will explain later. So basically, semantic search in the context of the web. So basically, it's what already large search engines like Google and Bing are doing for some of the queries. So I will like you to see that and discuss that before we go into semantic search, which has three parts: knowledge representation, how you ingest the content, and as Shalini said, we need to annotate that content. And then the key part is query understanding workflow. And then in the second part, I will basically go deeper on the query understanding part. So I hope all of you are familiar with machine learning. So I will give you just one slide crash course on the technology we will use. So we'll not have enough time to go into the models, but it's good to know how they work. So mainly people use what is called supervised deep machine learning, and in particular deep machine learning, which are neural networks that have many, many layers and billions of parameters. The most sophisticated ones have billion parameters. But these are not new. So these are from the 60s. So what happened today? Well, there were three important things that happened 10 years ago when this exploded. It started to explode. So we had more data, what is called big data today. We have more processing power. For example, we are using GPUs, which are originally designed for video games, and now they are being used for computing training the models. Even Google has something called TPU, which are specific CPUs tailored, in this case, to train TensorFlow. And then we can do, basically, thanks to more data and more computing power, we can have deep learning. Before was theoretically possible, but was not practically viable. So their techniques are not supervised, but they're not that interesting in the context of learning yet. They are semi-supervised, but the important ones are like the diagram here. Let me see if I can have a.
May I interrupt, Rick, 1 minute? I think
Yes.
your voice needs to be a little louder.
Okay. Sure.
Thank you.
So can you see my mouse, right?
Yes, we can.
Okay, great. So this is an example of a standard supervised machine learning algorithm. So you have a training set here that, for example, could be text, documents, images. For example, you want to recognize things in images, you will have labels associated to those images. For example, cat, dog, and so on. And then typically you will transform the content to some feature vectors, like, for example, if you have images, you can have color histograms, edges, and many other things that you can recognize an image and transform that in features. And basically, you will train a model that will try to predict the same labels of the ones that are in the training data. And that's the predictive model we have here. And now we see a new image, for example. We build the feature vector for this image, and using this model, we predict the label here. So we are crossing our fingers that this model will do well. So typically, you measure the accuracy. For example, 90% accuracy will be that 9 of 10 times this model predicts the right result. However, if the training data is not balanced, and for example, doesn't have an image similar to the one that we are inputting now, of course, that will fail. And you have seen maybe many examples of facial recognition issues and bias and things that I cannot talk today, but they are also important today in the ethics of AI. So there are some explicit training data. In this case, we have the labels, but also sometimes we can use implicit training data. And this is very important in the context of semantic search. And I will explain that later in the way. So basically, we can assume that the behavior of people can be used as labels. And this is very important because to do it at a scale, we cannot use only human-based labels because we need to label many, many more things that, for example, you can label in a few days by a few number of people. So let me give you an example of this. So a paper I published about almost 6 years ago. This was work done at Yahoo Labs, and this was considered the best work that year at Yahoo Labs. So this was trying to predict the next app that you will open. So we had data from mobile phones, and you want to predict what is the next app you will open. For example, if you can predict that, you can have the app really open, so you don't need to start the app. It's already there for you. Even if you know what the person will do with the app, you can even start that action. So here you see the basic case. So in black will be the basic features. In red will be using session features, so basically the behavior of people. and green is the combination of both. And here you see different techniques that we use. So for example, here you have naive Bayes, support vector machines, a clustering kind of, so basically another decision tree solution, C4.5, and then a softmax, and then a regression. And you see that, for example, the regression fails very badly, less than 10% precision. And for example, the softmax, you get more than 90% precision. And you have to use all the features. And you see that the session features is much more important than basic features like your data, your metadata, or the type of phone, or things like that. So the first thing I want to show with this example is that the technique that you use makes a difference. And there is no single technique that is better for all problems. So you need to find out what is the best one. Typically, you want to use a nonlinear technique if you want to do something more complicated. So that's why deep learning is the favorite here. And in this case, we had one distributed approach that is here. Something I forgot to mention in the previous slide is that one of the key things about deep learning is that you don't need to build the features. So basically, the system produces the features. So part of the prediction is also predicting the features. So basically, you can think that one of the layers on the deep learning architecture are the feature vectors that the system will use. But you don't know what they are. They're very complex, and they're basically predicted, like combining different signals to get the best possible result. Shalini, I don't know if you want to have questions in the middle, because I will cover different topics. So what do you think? If people want to ask questions, we stop, or because I will change? This was the introduction to machine learning.
Ricardo, we will stop towards the end. You speak for about 45 minutes, then we'll open it for questions towards the end.
Okay.
Okay.
So the other important context here is that the search is mobile. So this is the standard view of information retrieval system. So the person has an information need. You have some, for example, library system. You have the search system, and then you know that we have answers that are okay, answers that are useless, and that's why the precision is not 100%. And you miss some answers. That's why the recall is not 100%. Well, when you have the web, the main problem is the base. So the base is really, really large. It's dynamic. It's changing all the time. And then also people use search engines not only for information needs, they use it for other needs, and we will get back to that in the second part. And then we have the context. And the context is mainly what happens between the brain of the person trying to think how to solve the task, and, for example, the queries that you type. Most of the time, the information is lost there. It's lost between your transformation from what you are thinking to the queries you type. And the system cannot do anything about that. That's information lost in the user, not in the system. And of course, the context here is a mobile phone. So you have other things that you don't have in a classic desktop, like location. The direction of the movement, for example, is also important, because if you're looking for a restaurant in a car, maybe you want to give a restaurant in the front of your direction, not in the back. So you keep going in the right direction. Now, mobile search dominates. We will see later that around 2014 was the year when mobile searches became dominant. And you see here that for example, for last year, was almost 70%. So most of the time, the queries are mobile today. And that's because of many people have access to internet only on their mobile phones. Now, another important trend here is voice queries. And here I have an example from Cortana, the voice assistant of Microsoft. And now 10, 20% maybe of the queries now, 30% are voice between those, among those that are mobile. And here is something interesting on the number of words that people use when you do text search compared to a speech search. So you see that when people talk, the queries are longer. So in some sense, they are better for the search engine. Sometimes the words that don't help because they are like stop words, they are functional words like pronouns or articles and so on. But it's interesting that the typical 2-word average of text goes to a 3-word average on voice. And if people ask correctly, so they don't use stop words, that will be a better query. And of course, it's easier to talk than to type. Here is an interesting survey done by Google in 2014 about what people do when they use a smartphone as assistants with voice. And you see that most of the people that do this are young people from 18 to 29, so 71%, then 30, 43, 59%. And then if you're older, it's less than 50%. So people prefer to type or not to use voice. It's like in WhatsApp, some people prefer to send voice messages and other people cannot do it and prefer to type. Even that is slower, but I guess it's just different habits. Here you see the difference between what teens and adults do when they use the assistant. And you see that, for example, the teens will call someone while the adults will ask for directions, will ask for help with homework, while, for example, adults will detect text. So there are different behaviors, and that's why it's so important to predict, for example, the age if you want to predict what you are trying to do. So this is what I will get back to that. We need to predict the intention of the search. So, and the last part of the short course on the context is the distributed search. So we need to scale. We need to scale to billions of users and also petabytes and more data from the web. So what you can do is using this scheme to explain what you do. So basically you have two axes here. The vertical axis is the throughput, so how many queries per second you want to answer. And the horizontal axis is the volume that you want to handle. And the throughput is easy. You do replication. So basically you replicate in different parts of the world your base. And this is what search engines do. They have in North America, they have in Asia, they have in Europe, and so on. So a few replications so you can handle more users. And basically you can, with one replica, you can double the throughput. Now, for the volume, you need to partition the database. So basically you need to partition the index. For example, you can have an index for India because you have a large volume of users and you have particular content in 22, if I remember well, 22 official languages, which is a lot of diversity. So you need to maybe to have special indices in more than one character set for India. So what you do here is that you have clusters that basically handle every replica and every part of the index. So every partition of the index. And of course, more partitions, larger the index. And of course, I think I don't have here a diagram, but if you have a partition index, that means that you may need to search in more than one partition because you are searching in different parts of the world. However, if the query is just for India, you can maybe resolve the query just using the Indian partition, and I will get back to that in 1 minute. So there's something very important here that is caching. So you can cache answers, and this may answer like 30% of the answers today, and you need to refresh that cache. But it's very important because instead of replicating, caching helps on incrementing the query throughput in at least 50%. So this is very important and it's very cheap. Then you can cache part of the index too. It's not so cheap, but it's also important because in that case, the cache has a better performance because the index cache can go up to 90% success ratio. So here you have a typical large architecture, distributed architecture. So on the right part, on the blue part, you have what is done permanently here. So you crawl the data from the web, you parse it, you classify, for example, different types of text, and I will get back to this later on the semantic search part. But this is something that is happening all the time because the web never stops changing. And then you are building this index and you are updating the index periodically, for example, merging small index with large index, and so on. And then on the green part, we have the online part. So you have the user will go to a front end, typically kind of just the web interface. And then you will go to a proxy, and in the proxy, you find the cache of answers. So if your query is already in the cache, you get it back right away. So it will be very fast. And typically, if you have some news and people start asking about that news, that will be already in the cache, because you will have a cache for permanent queries, but also a cache for bursts of queries that happen in the hour. Now, if you are not lucky and the query is not answered by the cache, you go to the search cluster. And of course, here you have the different partitions. So here you can see that the child is one partition on the index, every child. And here you have two different search clusters, because this could be two different search partitions, or this could be two different replicas. We will talk about this in the next slide. But of course, search clusters cannot handle the whole index. You need to have more than one. So that's why you have very large data centers. Now, because you will get answers from different partitions, you will need to merge, to blend here the different rankings. And of course, the rankings are consistent. So there are ways to merge the ranking and send the final answer to the user. What is the main restriction here? This should happen in, let's say, less than half a second, because when you add the network latency, then you will have something like a second answer time, which is reasonable for most people. If you take more than 2-3 seconds, people will switch to another search engine. Now, to partition the index, you can partition by documents, which is the simplest way to do it, and it's what is used today. But you can even partition by vocabulary. So you could say, okay, let's have a search cluster that handles only the letter A, just to say an example, and so on. The problem with this, which allows to have more concurrency, so that you can increase the query throughput, is that indexing and keeping the indexing fresh is much harder, because basically for every change, you have to change the whole index. However, if you partition by documents, if you have a change in a document, you only have to change that partition. And this is the main reason that search engines today use a document-based approach. Now, how we can see the different architectures? They will differ in the number of data centers. So, for example, these search clusters, they will differ on how we assign users to data centers, and also how to assign documents, in this case, an index partition, to data centers. So you can think that here the case in the left is the centralized case. So everything is in one place, and every user is assigned to, for example, to a replica of this, sorry, of a different search cluster. Here you have replicated sites in B. So for example, this will be 3 continents, and then each user is assigned to each region. And then we can partition. And here you see that, for example, we can have users assigned to different partitions depending on from where the query comes. So the index partition in practice, I was saying, could be term-based or document-based, but document-based is the dominant one because of what I said, building and maintaining the index. Also, it's very easy to have load balance, and also you have more fault tolerance. And here there are 2 possible ways to partition. One will be geographic, the one on the top. This will be a geographic partition. But the more interesting partition that combines geography and language sometimes is better, because you have many queries that are in a single language, and you want to answer in only from that language. So you can have a combination of these 2 things. For example, you could have one in Spanish and Portuguese only for Latin America, for example. Now, if you do a centralized architecture, basically you cannot scale so well. And also you are spending, the cost is larger than it should be. So we did some work at Yahoo Labs to improve this. And we designed a whole new architecture to do a real distributed search engine. So basically, you don't have full replicas. And for this, we changed everything. So basically, we did local web crawling. We predict what is the best assignment to a user in the system. We did partial document replication. We did query processing with selective forwarding, so we predict where we should send the query to answer this task. So, for example, if you have a query that is in an Indian language, probably you don't want to send that to all partitions because most partitions don't have, for example, Sanskrit or other local languages. And the idea was to mimic the centralized architecture with less cost. So basically do the same, but because you are doing local crawling, because you are doing local processing, be cheaper. So it will be an example of like what is called today green computing. So we did a system in several countries with real data. And of course, you want to compute the best average response time. You want to have the same result quality. And also you want to measure query locality. For example, which is the fraction of queries that are answered by the system without having to send it to other partitions. Because if you can replicate documents and, for example, have very popular documents in your region, then it looks like local, although some of the data is not local. So you can optimize that. Basically, we had 5 different countries in the world where we put this system to test. And then we, of course, added the network latency and the query processing times proportional to the index size. And this was a paper we presented 6 years ago and shows how well you can do it. So here, in the graph here, you have the case of no replication. You see no replication, you have a 300 millisecond response time. If you do only 8% replication, you improve like 15% the answer time. Of course, we are having answer caching, so that's very important. This is the one in blue, global, and this is the time to live. So basically, we refresh the whole cache in 2 hours. This is important when you have news. And then the case of no caching. So you see that the blue here is no caching, but then if you go to caching answers, you increase another 20% of the answer time. So this is very important. So you can see how replication and caching, you get basically a 50% improvement on this. And here you have different ways to predict where to send the query. So you have a linear programming solution. This was a previous paper of us. You have a machine learning solution, and you have the Oracle. The Oracle is the one that knows exactly where to send it, and this is our what we want to get. And you see here that at the end, we could do very well, not too much different from the Oracle, getting an NDCG of 0.95, 0.99. So this is measuring how well we are simulating the answer from the centralized system. So if you get 1, means the same answer. If you get 0.99, means basically that from 100 queries, more than 99, because this is a weighted scheme, more than 99, you get the right answer. So this proved that you can simulate the system, getting almost the same answer and spending less money. So this is the way to go, and I hope that in the future, all search engines should go this way. Maybe they're already using these ideas. They were published like 5 years ago, but these are trade secrets. So before I enter on the semantic search part, I would like each of you just to search the name of a person in your favorite search engine. I want you to do this exercise before starting this. So go to your favorite search engine and just search for a name of a famous person. And after, let's wait 1 minute so you do that. You can tell me in the chat what you saw, what you see, anything special there. So what you should see there, if you search for a really famous person, is you see what is called, for example, you're using Google, a one box that is in the right side that has typically information from Wikipedia. This will be a semantic answer. So the system understood that you're looking for a person, that the person is famous, and then that can be found, for example, in the Wikipedia or in another annotated database, and chose a summary of that. And usually that summary is done automatically. So there's no human intervention. This could go on in a philosophical discussion if we should have humans in the loop or not in the system, but that would be a different topic. So let me 1 second. So then let's go to the semantic part. So if you want to do semantic search, you need to have some knowledge resources. And there are 4 important knowledge resources here. The main one is an ontology. So typically now it's called a knowledge base. A knowledge base basically sometimes is all these 4 parts together. It's called a knowledge base. But you need an ontology, so you need to represent the world. And I will give you an example in 1 minute. Then you will need a lexicon. I will explain why you need that. Then you need what we call, when I work on intent, onomasticon. I will explain what's that. And finally, you need some linguistic rules. For example, you need a semantic representation, standardized, something called case frames. I will give you an example. Now here I have this LI and LD, that means language independent or not, or language dependent. So the ontology and the onomasticon are mostly language independent, or the ontology, of course, is language independent, but the lexicon is language dependent. And that's one reason to have the lexicon, because you may need to translate things from one language to another. So typically in the ontology, you will use one language, for example, English, and you will have to translate everything to that language when you want to use the ontology. And in this case, English will be the best choice because we have more translation tools for English. Of course, for example, Wikipedia only exists in 5% of the 7,000 languages that are alive today, many of them in India, by the way. So why the lexicon is language dependent? Because you need one lexicon per language. So basically it will be the mapping from that language to the ontology. So for example, you can have as I said, the ontology in any language, but you want to know what is the entry, for example, for cheetah in the knowledge base. And you will have, basically in this lexicon, you will have this mapping. So for every word, you will have a mapping to the ontology. You may have more than one expression associated for each concept from the ontology. So you have synonyms, and you want to have that in the lexicon too. You will have expression-specific attributes. And for example, in my work, we had, for example, 3 different languages for a single ontology. Here I have an example of how you will represent different lexicons, the cheetah concept, and you see that in these 6 different languages, the representation is different. In the Latin language, it's very close, like in French, Spanish, and Italian. But for example, in Romanian, which is also a Latin language, but they use a different character set, they use a Cyrillic, then looks similar, but it's really different. And then you have, for example, something completely different like Chinese. Now, so onomasticon is mainly for entities. So because not only you have words coming from a dictionary, but also you have people, institutions, and other things that have a name. And these are very relevant to search. And this will be mostly language independent, but sometimes this is not true. For example, here I have an example of Lady Gaga. Lady Gaga in almost all languages have the same name. So no one dares to translate her name to other name, but it's not always true. We know that sometimes even, for example, toponyms, like city names, they're translated. Here, for example, is Geneva, and you see that you have different versions. Even in Latin languages, they change one letter. And of course, you can make a mistake if you know these two languages. So we need to have these distinctions that go beyond the knowledge base. Now, the linguistic rules, they will look like that. This will be basically XML templates in a special language. So we had our own language to do this. And for example, here you can see that you have a context of lunch or dinner, and you want to select the kind of cuisine, and then you return a list of restaurants. You see that if the concept matches dinner, or the concept matches lunch, or the concept matches cuisine, and here you have or ethnicity, then the interpretation, for example, would be a list of restaurants, but for that cuisine. So this will be one linguistic rule. Basically, we're saying that if we find this in the query, then we will assume that it's a restaurant search. In this case, there is no machine learning. It's a fixed template, and this will help for a big percentage of the queries because people use the same structure when they search. So here, it's another template. So basically, you can have many templates like this for different things. For example, this one is more complicated, but has to do with buying pizza, donuts, and so on. So typical things people buy in the US. Now that we have all these elements, I can explain what is the difference between the search engine we had before and the semantic one. So the first thing that we will have to divide in the second part, we will get into this, we have to divide between concepts and entities. So things that are common nouns and proper names. And then the semantic engine will use these semantic resources. Remember the ontology, the lexicon, the onomasticon. And the semantic rules and the semantic representation will be here on the interaction between the semantic engine and the knowledge base. So all this is on the right is the knowledge base. Now, what do we need to do? What are the functions we need to solve? And in many of these we will need to do machine learning. I cannot go in detail into this, but if you have questions, I can ask them. Sorry, I can answer them. You need to do first many times language detection. And today with machine learning, you can get a very good accuracy, over 95% for most languages. Then you will need to do boilerplate detection and removal. So in the context of the web, or in the context of a page of a book, that means taking out everything that is not important for the index. So if you have, for example, you are indexing a magazine or a web page, you want to take out advertising, menus, and everything that is not really the content of that item. Then you will have to do tokenization and lemmatization. So I assume that you know what is that, basically extracting every term and then every lemma of the term if you want to if you don't want to deal with say plurals and different verb conjugations. Then you need to do part of speech tagging. So here we are doing natural language processing. So we need to understand the grammar of every sentence. And for example, what is the subject, what is the action, and so on. Then you do morphological analysis, so a bit more deeper natural language processing. And then we have to do entity extraction. This is the most important part, because basically sometimes the whole answer is based on the entity, like the example you tried with searching a person. And we may need to do a general dictionary matching to see the concepts that are in the query. So basically here you are matching the entities and the concepts. Then you need to identify the concepts and disambiguate them. You may have you may have many topics related to a concept, to a word, sorry, many concepts related to a word. So you have polysemic terms, and I will give an example later. And then you finally need to do the standard ranking and maybe classification if you want to split documents in different ways and so on. So I will get more in detail in the concept of identification and disambiguation, which is the main part of the semantic search. So just to make sure you understand what is boilerplate detection, here you have like a typical web page, and the boilerplate detection will be basically to delete everything that is in red. So I will do it again. You delete all that, and you keep only what is relevant to, for example, this news, that the title, the author, the pictures are relevant if you are doing image search, and the text. So this yellow part is what you want to index and not the rest. Otherwise, you will get a lot of noise, and you will get basically precision will go down if you don't do this. Now, very important here, I don't know if you can see that is underscored in red. You have, for example, finding some of the entities, like Golden State Warriors, that's an entity, which is an NBA team. And then you have Western Conference Final, that's another entity, that's a competition, and so on. So you need to detect these things here. So to extract entities, you have attested entities. So basically, these are entities that you already know, things like people, places, organizations, brands, works of art. These things could be multi-token. So for example, United States of America will need 4 tokens. Sometimes it's just United States, sometimes it's US, sometimes it's USA, and so on. So this may need to be very carefully done so basically you don't miss any represented entity. And then you have unattested entities. So basically entities that you don't know, but using machine learning, you can predict that these are entities. For example, you can infer people, like for example, a mayor. You can infer a place, like a hospital. You don't have that hospital, but you understand that in this context, the hospital is not the noun generic hospital, it's a specific hospital. For example, Mr. and things like that. And this is what is called machine learning based name entity recognition. So you will see this acronym to be used for this part. Of course, this is language dependent. So sadly, there are no good name entity recognizers for all languages, but for the main languages, you have very good resources. Maybe for many Indian languages, you don't have it, but I believe that at least 5 or 6, you have good name entity recognitions. I did some research on that, so if someone is interested, I can send that to a table of resources on different Indian languages. And then you have other entity types that may be important, like phones, monies, date and time, etc., that you need to keep track, because, for example, time is a very important attribute in many search queries. For example, you don't want to give a document that was valid 1 year ago if you can infer that was that the query is about today and not about the past. Now, when we do the classification part, and basically we analyze documents, again, we can combine rule-based and machine learning classification. And here we can classify in many different dimensions. For example, here are some dimensions that are important for semantic search. First, the topic of the document, for example, health, politics, and so on. A particular aspect around the topic, for example, entertainment, place to stay, restaurant, weather, So this will be, for example, something important for travel. The genre is important. Sometimes people mix topic and genre, but which are not the same. So even in some well-known taxonomies, they mix genres and topics, and they shouldn't be mixed because you can have the same topic in different genres. For example, you can have politics news. News will be the genre, politics will be the topic, but also you can have a politics book, and so on. So here are some possible genres. Then you need to identify things that may be important for sensitive issues, like is spam, is adult content, is offensive content, maybe related to some addiction, for example, to weapons, gambling, things that you shouldn't say. So this is very important today, especially with false news and other things. Another thing you can do is reduction quality. So there's a few techniques to score the quality of the text. For example, how good is the grammar and so on. By the way, if it's fake, probably it has very good grammar. So it's not, that doesn't mean that finding well-written articles mean that they are true, because people take care of writing those very well. And finally, we can extract other things from documents. For example, in the web, we need to extract links, for example, typos, and maybe we want to, if we are sure, to give the right terms there. If you have a shopping cart, if you can do login, if you can download, and so on. There are a lot of things that you have actions in a page which are important for people when they search. And that's why it's so important to have semantic search, because if you have a mobile search results, most of the time you don't want to have here, like in the right side, 10 blue links. You don't want to have 10 blue links. You want to have a semantic answer. So here is from a real system I work on. So for example, here the query, if you can read it, is what about lunch in Encinitas at noon? So Encinitas is a place north of San Diego. And the system understands that you are looking for a place to have lunch. So doesn't make sense to send you to 10 blue links. So the first answer here, the first semantic answer is a map. And then you have a list of places where you can go. This, for example, comes from Yelp. So that's a very important thing. The semantics answers come from different sources, and you need to merge the different sources to have the best semantic answer. Here in the right, you have another query. It's a science fiction movies playing this afternoon in Carlsbad. And then the system understands you want to see a movie this afternoon, and what gives you? Well, gives you the movies that you can see this afternoon in this place. So most probably that's what you want. Now, how we know if we have been successful? Well, if the people clicks in a movie, you are successful. If the people clicks in other thing or does something else, maybe you are not successful. Not always the predicted intention is the right one, but in this case, probably it is. The same here. For example, if people click in the map to explore, or clicks in one restaurant, even scrolling this, and remember, today you can log all these actions, then you can find that the person was successful. So the question is semantic processing enough? So let's say, what about lunch in Barcelona at noon? So the system will have to extract at least 3 different things that are important. So lunch will be a concept, Barcelona will be an entity, and noon will be another entity. It's a time entity. So this is a location entity and a time entity. So is this enough? Well, not really, because here we just have 3 concepts, but these 3 concepts can be used for different things. For example, you can say, I was in Barcelona before noon for lunch, and that also has the same 3 concepts. Or for example, I can say, don't go south of Barcelona after noon for lunch. And of course, in this one, the action is lunch. In these other 2, is not. One is in the past, another one is a recommendation for the future. So we need to do more. And this is where syntactic analysis and semantic representation, these templates I show you, are so important. You need to understand verb and the roles associated with a particular interpretation of a verb. So you can say, for example, Ricardo bought a watch at the store on Monday. And then, for example, here you have an event. So here you are predicting an intention, like it's buying. You can say purchase, acquire. So all of this has to be mapped to the same concept in the ontology. So in the ontology maybe buy, but all these three should work the same way. Then you have a subject, it's a person, recognize that that's a proper name. You have that the role is an object, so it's a physical object, it's a watch. You have a location, it's the store, and you have a date time, which is Monday. And the system has to recognize all that. So that means that you need to do a semantic reduction, and this is the key part that will help you this ambiguating. So for example, if you say lunch in Encinitas at noon, you will have this standard semantic representation. So for example, interpretation for a meal plan. So meal plan is anything related to, for example, going for lunch or dinner and so on. And then the action is a restaurant action. And then you have all the attributes of the query here. So for example, we have a location. We have that there's a local query and so on. So you have open hours is noon, categories restaurant, categories product categories lunch and so on. But now this representation should be standardized. So if you have all these different things, all these ways to ask the same question, and these are real examples of how people type the same query. So you see, especially in voice, you will get this kind of queries. All these variants have to be represented in the same way of this simple version here on the top. So, and of course, you can have many more. So the diversity of how people ask things is amazing. So all these are reduced to a single language-independent formal interpretation, and this will be the prediction. So for example, you will say, okay, this is the representation of all these queries, and for example, I am pretty sure with 80% confidence that this is the intention of the user. And then you will have expert answers. So the query will go to the interpreter that will do this work, will get the formal interpretation, like the one that we was just shown. Here we are using, of course, the knowledge base and other information. And then we will need to call different experts. And we will call here expert to one particular semantic answer. For example, one expert could be famous people. Another expert could be weather. Another expert could be, for example, money exchange, and so on. So instead of trying to have one system that answers everything, after predicting the intention, you have a system that is specific to predicting that intent. And this works much better because if you did the right prediction, then you have the right answer. Also, in some sense, you are doing divide and conquer because you are splitting the prediction part with the answering part. So you can have things like, for example, you can use different sources like Yelp for local business listings. You can use the local providers. I'm sure in India you have something equivalent or more, maybe more than one. For example, you cannot use Uber if you want to call a car. In India, probably you have to call Ola and so on. AccuWeather for weather, there are many providers. Stats.com for leaked sports data, and so on. So you have all these providers also of very good semantic answers that you can use and do different business deal with them. Some people just want more traffic because they have advertising. Some people want to be paid for the data, and so on. Maybe paid for by query, and so on. And these are just three different examples. So you have three flavors of expert. You can have an external API call. So you use another service to get the answer. You can ingest data from third parties. So basically, you are, let's say, paying for accessing, for getting a copy of that data, and then you use the data locally, so that's faster than using an API. And finally, you can have your own expert data, of course. And this case will be the knowledge base that you already have. For example, you don't need to have everything. You need to have what is most used. So for example, if you have, let's say, 500 million concepts, that will be good for more than half of the queries, even more. So, so this will, let me explain this diagram, and I can end here the first part for questions. So this is the mobile query understanding workflow. So it's putting everything together. So here you have the user. The user has a context. So the context is things like time, location, device, history of queries, and so on. And here on purpose, I'm doing a very silly query, but it's ambiguous query. So the person wants to see, let's say, a James Bond movie, and he's lazy and just writes Bond. The first thing that will happen in a modern search engine is query autocompletion. So as you type, you will get possible answers. So if you type just B, maybe you get Bing. If you just type BO, Boston, and so on. And of course, if the person clicks here, that means that you're doing that very well. So this will be explicit feedback that is positive to train the system. So if someone clicked in a completion that is suggested to the user, then that's good. Now, also you need to do a spelling correction. And spelling correction has basically three kinds of outputs. One is no need to correct. Second is, I'm not sure if I need to correct, but seems that there's a mistake, so you suggest the answer in different query. And the third one is, I'm sure that the user made a mistake. I will change the query. Of course, if you haven't made a mistake, you don't get happy about that. So you need to really be sure about that. And there are classic examples where that fails. For example, people that is called like Schwarzenegger typically get Schwarzenegger, although they are not Schwarzenegger. Then you have a semantic analysis, which is that's all these things that we have been talking about. And one important thing here with semantic analysis, you can do semantic query suggestions. So these are the same that you get at the bottom of a page in a search engine. Typically, these are much better than query completion because they may have a different prefix, so you don't need to have the same prefix. And here you have to focus on freshness, diversity, novelty, and serendipity. And here you can have things like investment bond, James Bond, bond chemistry, bond band, even things that don't have the word bond. That will be a really, truly semantic suggestion. Now, of course, the context will be very important on the intention analysis part. And here you have a possible result. For example, the system predicts its information with 70% score, transaction with 30%, and inside each one, for example, you have movie definition music or financial movie music. So basically you have all possible intentions across all types of queries. And of course, this is an ambiguous query. And then you get to the probabilistic disambiguation of the ranking, and you get to the last module, which is of course machine learning based module, which will be an intention ranking. And then you get, for example, here that there are 4 intentions with different confidence. For example, movies, news, music, and definition. And this is the ranked order. So believes that the most probable is movies, the second one news, and so on. Now, for each one of these, we have another machine learning module that does the ranking for that kind of intent. So like in the classification process, we use a specific ranking modules because we already know it's a movie. Because ranking movies, for example, is very different from ranking, for example, news, very different. And here, after the ranking, you have the answers. For example, for a movie, you will have on the top a semantic answer that will be the one like I showed you of the Bond movies that are shown today, if there are such movies. Otherwise, we say, okay, maybe the person wants to find what are the best Bond movies, and you get the 3 top Bond movies as answers. These 2 are semantic answers. Then, for example, you have news. Then maybe you want to have two top news related to financial things, unless you have a new Bond movie happening, which could be true. This will be more like a standard ranking of 10 blue links. For example, in music, you have to rank music, and here you have, for example, Best of Bond, which is a UK string quartet, so you have a polysemic problem, and you need to know that from your knowledge base. Of course, you can have the Best of James Bond soundtracks, or for example, you can have a conversation with a very famous broadcaster in BBC, which is called Graham Bond. And finally, definition, probably if you are looking for the definition of Bond, the first one will be finance, then a chemical bond, maybe the next one will be bond paper, and the last one will be Bond Street, which is the equivalent of Wall Street in London. So you see that this is the whole thing, and you see that the machine learning is involved on query auto-completion, spelling correction, semantic analysis, the query suggestion, intention analysis, intention ranking, and the intent answer ranking for every kind of intent. So things that you will see in the future, things as a service. For example, you may have a service just to extract entities, a service just to do local search, a service just to do semantic understanding, a service just to do intention prediction, because I imagine in the future there will be companies that will be specialized in one of these sub-problems that we have here. So we have many sub-problems that basically help us to solve the whole semantic search pipeline. So I don't know, here we can do the first break, or the only break.
Yeah, this is the first break, or the middle, actually. Okay. Yes. Okay, thank you so much, Ricardo. Now we are open for questions. There was one query which was put on the question
can we take the queries for raised hands? 2 people have raised their hands.
They have put up their hands. Okay.
Yes, yes, yes.
Then you enable them, then they will ask the questions.
Priyank Taparia, you have been unmuted. You can unmute yourself now. You can ask the question.
Priyank Taparia, unmute and then ask a question. And then I see Mohammed Minhaz. Minhaz, you can go ahead.
Okay. So first of all, thank you for that insightful talk. My question is related to the search engine architecture that you explained. You mentioned about the index partitioning as an important technique to improve the performance of search engine. And say in case we partition based on, say, a region, it will take care of probably the speed of queries. But when it comes to the accuracy, will it not involve again a partitioning approach or different approach for different actually regions? If you're talking about a web scale kind of a search, because the search behavior itself may be different. So how do we address that issue, sir? If you could kindly throw some light on that.
So let me see if I understood exactly the question. So basically you are saying that the accuracy is not as good because of the partitions, or because you don't have the right partitions?
No, if I've understood right, partitioning is only in terms of the knowledge index partition, right? But in terms of the search understanding, the semantic understanding of the search queries, will that also require a partitioned approach, or you're talking about a uniform approach being used? Okay,
so in the standard case of a search engine today, the partitions are not semantic, if that's your question. Yeah. So typically the partition will be more based on language and geography. They could be logical partitions. They don't have to be really physical partitions like in different data centers. They're logical partitions. Now, if I see the future, I would say that if you have if you can predict, for example, the topic of a query, for example, you know this query about say COVID, will be very good if you have a semantic partition of, say, all the content about COVID. So this is something I think we will see in the future. but today we typically it's not that, because also you don't need to have a real partition for that, because if you have annotations, you can have annotation like saying this document is about COVID, and then you just do filtering to get the right logical partitions. So I think you do physical partitions for performance and for handling very large amounts of data, and then you can do logical partitions for the semantic part, but this will be done by software, not by real physical partitions.
Okay. Sure, sir. Thank you.
Rick, I have a question. Can I ask a question?
Yes, of course.
Because Priyank Taparia is not ready yet. Anyway, I'll ask my question. You also mentioned, and my understanding is most of the search engines maintain only the recent queries, right, of the user, or all the queries, entire past history is maintained.
That I cannot tell you exactly, because I will need to be there working for those search engines. But I believe possible they keep all your history, but they give different weights to the history. For example, typically you have exponential decay. Now, if you are in the EU, there you cannot keep the queries for more than 18 months.
Okay.
So in the best case, they can have your last 18 months. Now, it's very important. It's very interesting your query from the point of view of change of behavior. For example, with the COVID, the queries change a lot. Like more online shopping, different kinds of worries like COVID itself and so on. So if you don't do this weighting properly, your ranking deteriorates very fast because there's change of behavior. So I would basically not delete your queries, but I will like split the queries in different behaviors. So I use the right history for every query. But I don't know if search engines go in such detail of handling or of doing like a mini knowledge base for your queries, because you can do that today. So that's a possibility.
Are they creating some kind of a profile of each user?
Of course. I mean,
each user has a profile, right?
Yes, all large search engines, so not only search engines, all large websites like social networks and so on, keep a profile for you, and so even if you are just a cookie.
So basically, my profile is there, so the intent generally can be predicted much easily, right?
Yes, of course. One of the context, maybe I should put it there, is a profile. So in our case, we don't use it. So we were trying to not use a profile. So we were trying to do semantic search without endangering privacy. I have something about privacy at the end of the second part, okay, because that's very important. So personalization is good, but basically you are less private. And no personalization, you lose quality on the ranking, but you're private. So there is a trade-off there.
Okay, thank you. So is Priyank ready? There was a question, right?
No, I guess.
No idea. So, but can we read the question otherwise, right? There was this question. Yeah. Let me read.
Sure.
The Priyank Taparia's question is, in essence, accuracy of the search engine would be determined by the number of clusters that have been created and the relationships developed. More the complexity in search, more the clusters required.
So it's more like I think it's a comment, not a query, but
okay.
But I would say that it's true that more complexity, more clusters, because the truth is that the clusters don't depend on the complexity. The clusters depend on how many users you have and how large is the data. So it's not really based on the complexity. So I disagree a little bit that the accuracy depends on the number of clusters. So accuracy is something independent. So clusters are basically how you handle a scale, not how you handle the complexity of the problem. So they are separate problems. So you can have very bad accurate, so you can handle very large scale and have very bad accurate, or you can be very slow and have very good accuracy. So it's not, it doesn't depend on the hardware, that part. Of course, you will need hardware to very powerful hardware to do a better accuracy if you want to do that. So for example, you're using deep learning. For example, I didn't talk too much about ranking, but for example, typically ranking is done in a two-phase approach. Then first you do a very simple ranking very fast. You select a few thousand candidates, and then you apply a deep learning ranking to those candidates, because you cannot do deep learning ranking for let's say more than 10,000 answers. It will be too slow. So you have a two-phase ranking approach for almost all rankings that you do today.
There's one more question from Mohammad Minaz. Please ask the question, please.
Minaj, go ahead
Sure.
and ask your question.
Sure. Sir, in the initial section of your talk, you emphasized on the challenges associated with feature engineering. I mean, identifying features for classification, etc. So related to that, I was curious to know the suitability of using ontology for semantic understanding of queries. Because in your explanation, you also mentioned that ontology is language independent. So if queries are given in different languages, and if ontology comes into picture only after the translation happens, don't you think the essence of the context is lost? Your comments on that, sir, please.
Oh yes. So this works only if you have language support. So for example, in India, this is a very big problem, because you have 22 languages. You may not have knowledge bases for all these languages, official languages. So you have many more. I think you have 600. And then you need not only to have support on the knowledge base, you need to have support on the natural language processing part, which is even worse, because maybe you have knowledge bases for say 10 languages, but then you have natural language support for only 5 languages. So in that case, what you need to do is what we call shallow semantics, in the sense that many things can be inferred without knowing the language. And this is a very good question, because I will talk about this the second part. So how you can extract more semantics without having the knowledge base, only based on the behavior of people. So because behavior is associated to semantics, so you can use that to basically infer things automatically that you will not be able to infer because you don't have, say, a knowledge base on that language. But this is one of the main problems today. Also, for example, let's say I'm guessing, but maybe in many Indian languages, there are some words that are very similar, but they mean different concepts in different Indian languages. That's another problem, because you need to disambiguate there, and maybe very hard to disambiguate if the two languages are spoken in the same region, for example, because that's part of the context. Yeah, but this is, of course, this is a limitation of semantic search. You need to have knowledge base support and natural language processing support for every language you need to handle.
Thank you, sir.
Can I ask a question, Professor Baeza?
No. That's a joke.
Yeah.
Of course, you can.
Can I ask a question, please?
Yes, of course.
Okay.
I was joking.
You mentioned that most of the users use a maximum of about 3 keywords. That's the peak. And most of your examples you picked up were from Google. The Google backend, Google content is largely unstructured in nature. I'm referring to the Google which is largely used by consumers, not Google Scholar.
Yes.
Now, when it comes to, in this group of participants, there are a good number of librarians who come from the world of structured content searching, unlike typical Google search, which is largely unstructured content. In a structured content environment, the search evolved largely based on Boolean logic. And now in Boolean logic, again, for most of these knowledge resources, which are fairly well structured, there was a basic search, there is a basic search, there is an advanced search. Now, if you, question number one, if you implement semantic search, do you think advanced search is irrelevant? You don't need to have anything called advanced search at all?
That's a good question, because today advanced search is used very little. So I don't have these are statistics that are not published, but in my experience from being in Yahoo and other things I implemented, advanced search is not used too much. Because really the reality is that most users of the web are not like the people attending this course. So they are not familiar with many things, like, for example, they're not familiar with Boolean logic to start with. So maybe advanced search is used by 1% of the people. But my argument will be that you need to have advanced search, not because people use it, but because you need to have it because it's a functionality that people expect to have it. So this is like something that maybe is useless, but you need to have it. It's like, for example, imagine a car that has something that is never used, but the people will not buy that car if it doesn't have that. It's similar to that. So sometimes you need to have certain basic functionality because the field already said this is like something core to the technology. And sadly, I think advanced search, well, not sadly, because there are always power users that will use it. But of course, what is true, I think if you have semantic search, less people will use advanced search, because now even more, you will have better answers. But for example, I can imagine, I would like to have an advanced semantic search, because for example, I may want to say which kind of entities I want to find. I want to maybe to specify things that are impossible to do today, like time, sometimes geography. For example, maybe I want to say I want the person mentioned in the document, and so on. So I think we should have it too. Less people will use it, but will be important.
Okay. Yeah, continuing this, my question, when you look at the search, search by scholars, largely the researchers and the academicians, their search is largely scholarly in nature. Let me call it scholarly search. Who are used to searching today, largely using Google model of searching. They don't generally use advanced search, but scholarly search is largely iterative in nature. In consumer search, largely you give a couple of keywords, pick up whatever comes in the first 2 pages, and if you get something good, you feel happy and you exit. And whereas in case of scholarly search, it's iterative, and you continue the search until such time you really find what is relevant to your work. And there, what happens during the Boolean search time, which is still used for structured knowledge resources, the user has a better control in defining the search query through advanced search. And the problem with the advanced search is, as long as you are using the only 2 levels of such queries in box number 1 and box number 2, the machine is able to follow fairly well your sequence of input. Now, the moment you introduce more than 2 such boxes, it will be difficult and almost it's impossible to match the sequence of the intent of user in terms of sequence in which he is submitting and the way machine will understand. Now, in this situation, advanced search completely fails if you have more than 2 such boxes. And this can be demonstrated through a set of queries. Although most of the knowledge resource based service providers, database search platforms, they still continue to support more than 2 such boxes. Now, if you mentioned about semantic search based advanced search, in that scenario, how do you really give the user the experience in terms of UI. Now, if you give the user too many such boxes, he will really get confused. The machine will not be able to understand the query. And that is where the complexity arises. So do you have any suggestions here?
Yeah, I think that there's we're in the beginnings of semantic search, and I think that's a very good question. What will be the right UI? So, for example, maybe you don't want to have a search box, but maybe you want to have like users like us. Maybe we want to have a graph where we specify the knowledge we want to find. This will be one way. For example, if you are searching for some relation, it would be much better to do a small graph specifying the relation and then trying to match that. So you have either the way that this doing today, that where semantic is something the user doesn't see but is used, so like a seamless semantic approach, where it's used but you don't people don't see it. On the other hand, for people like us, you would like to be more powerful and specify those relations, because when you don't see it, maybe the system will make more mistakes. So the accuracy of the system will not be as good as if I give exactly what I want. For example, sometimes you have relations that they're very hard to represent in a query. For example, you may remember that you want to see a page where you remember that was a figure, and that was on the top and was in the graph. You don't remember the page, but you remember a lot of the context, which is like more about the form and so on. And today it's very hard to do that kind of query. So that's why I think we need to work on completely different user interfaces to specify this kind of relations. But I think there's almost nothing to do that there. So that would be a very good topic for a master thesis, for example. So can we do like a short break?
Yeah, I think we go for a break now. So we have exceeded the first session break. So we give half an hour break and then reconvene at 5. Is that okay, Ricardo, for you first?
Yeah, perfect, yes.
Okay, so participants, thank you so much for your patience. We extended the time a bit here. So I would like you all to be here or come back at 5, okay? So we have another second session of this this workshop. We begin at 5 p.m. Hello, welcome back. Professor Ricardo Baeza, Yates, you are back. So we are happy. I suppose most of our participants are also back. So we start the second session. So you go ahead.
Yes, I will share the second part.
Yeah.
Okay, so I will start the second part.
Please go ahead and start the second part. It's about inquiry analytics, right? Yeah.
Oh, yeah, inquiry and understanding, yes.
So once again, welcome back to all our participants. Thank you so much for staying with us. And I suppose many of you who have taken the break will come back, okay? So we still have 60 and odd participants still here. Go ahead, Ricardo.
Yes, so in the second part, I will basically do query understanding. So I will briefly talk about users and behavior and tools, so how people, which people and how people use search engines. And then the second part of the last part of the second part will be on query intent, query mining, where I will talk a little bit about how extracting semantics without knowing the language, which was one of the questions that was at the end. And then I have a couple of slides on what are the issues with privacy. So today we can record a lot of behavioral data. especially mobile phones. So we have queries, results, the context, what device we're using, when, time, location. We have clicks on results, so we have metadata like the rank of the answer. We have the dwell time. The dwell time is how much time you are seeing the answer. Of course, you know that only when you come back to the search engine. So in many cases you have unknown dwell time, so you know that you went there, but you don't know how much time you were there. But with a good fraction of results, we have the dwell time. And the same, we have the query history, like for example, reformulations. We have browsing on the result side if we instrument the query that way. And even with some more work, we can have mouse movements, text selection, tabs, and many other things. So the main problem for a new search engine is not the technology, are the users. So getting the real users. So today, the ranking is done via the behavior of people. So if you don't have 1 billion users, it will be very hard to come up with a very good ranking. And this is the main barrier of entry for a new search engine. So if you have real users and real data, you can do much better than anyone else. So here are some challenges, like make the system usable, make easy to run evaluation experiments. So we'll talk a little bit about that. And there are two important considerations: privacy, we'll talk that about the end, but also the ethics when you're using people to improve your system. So people is willing to basically to give away this data to improve the system. So the possible ways to get this data depends if you're a search engine or not, but also depends on how you instrument this. So you can have a web proxy. So for example, you would like to improve the ranking of your own search engine. You can have a web proxy that gathers the data for your, say, company or institution, and then you have these logs to do better. You can have a browser toolbar. There are many toolbars today that are used by search engines and also by browsers. For example, Firefox has a toolbar and so on. You can have a search engine on top of a public search API. So this will be like a syndicate search. And then if you do that, you can get all the data, although you are not doing the search yourself. And basically, you can do your own search engine. Will be the hardest way to do it, but this is what is done by the main search engines. But for example, there are some very well-known collections like Archive, PubMed, medRxiv, and that they do their own search engines and are quite good. Wikipedia, because they want to provide a good search experience to people. So here I recommend, I can send these slides to you later, Shalini. I recommend some interesting talk in one of the Data Libraries Conference 2007. That was one of the first that looked at how to study users. But now we will go very quickly to who is the audience of search engines, because sometimes this is important to understand. So the first thing is number of users. And here, again, we see this break-even point that I showed before, that in 2014, mobile users become larger than desktop users, and then you have more mobile queries than desktop queries. So today, easily we have more than 3 billion people that is using search engines in the world, maybe even 4 billion, which is currently the number of people that have access to internet. Here I have some data from 2019. So where are these users? So half of them are in Asia. So half of them are China, India, Indonesia, Bangladesh, Japan, which are the very large countries in population. And you see that the second group is in Europe, then it's Africa, then Latin America, North America is only 7% now. That includes Mexico, US, and Canada. And then you have Middle East is part of Asia, but here is given. So from where? So now here you have some results from our work in data that gives, in some sense, the internet penetration of every country in 2017. So you see that developed countries and also South of South America have the largest penetrations in the world. And you see that the lowest penetration is in Central Africa, and then in places like India, for example. If you take the number of people that don't have internet access, the largest number of people is in the sub-Indian continent. So there's 1 billion people that in India, Bangladesh, and Pakistan don't have access to internet. So this is the focus point of where we need to work to get internet to all people. Especially with COVID, clearly internet already has been suggested as a human right, but with COVID, especially to study and to work, it's clear that that should be a human right. What age the users have? I mentioned this a little bit before, but mainly it's young people. So 50% of the users are less than 34 years old. These are data from 2014, but that hasn't changed much in the last years, even gets more biased to young people. Then some examples of demographics. So for example, here you have also ages, but also you have ethnicities or races in the US. You have also gender, more male than female. That's true, and also in social networks. In most social networks, the majority is male, except in, for example, in Pinterest. In Pinterest, there are more females. And here you have different regions of the US with different penetrations. For example, you see the lowest penetration in the US is in the South.
Ricardo, may I interrupt a bit?
Yes.
People are saying that they are not able to hear. Can you raise your voice a bit, please?
Okay, maybe it's the place where I have the microphone. It's better now?
Now it is better, yes.
Yeah, the microphone goes a bit back, and then I guess it's not so good. Sorry. I will have it in my hand. Yes. So there are 3 points of view of user behavior. So there's a micro level. So the macro level is the lowest level of details. So it's at the millisecond. So basically every click will be here. Then you have what we call the meso level. So this is basically what people do in minutes and days. And then you have macro level, which will be minutes of observations, where you go from days to months. So for example, if you want to understand seasonal behavior, you need to do the macro level. But if you want to understand, for example, if the search was successful, you need to the micro level, so on. So there are different ways to this. And of course, there are different ways to study this. So for example, meso level will be typically field studies, where you have people doing like a session of 1 or 2 hours, and you maybe videotape them, and you even ask a survey after, and so on. Session analysis will be macro level. So basically you want to analyze sessions across days and even across months, basically what people do in the logs. And for example, if you are not instrumenting your search engine or your search interface, you can do even micro level using eye tracking studies. For example, this here, the middle figure is an eye tracking study where you see where people focus when they're searching. And these, for example, these crosses here, these are where the eye was focused during the search. So I have like a summary of these different kinds of studies. So interviews held in situ. Many times you have special locations to do this because you want to video people from other different angles. So here you want to see things like how ads affect the search, distraction, multiple tasks, ambient noise. They will depend on the experiment. Then you have eye tracking and usability. Here is an example from Google. This typically will take some weeks, and you have 3-5 researchers observing what is happening. And this could be to understand what is the impact of new UI functionality. And eye tracking will be the one that gets really deeper understanding. So many times we are not conscious on how we move the eyes and how we focus, and eye tracking can capture that. So here are examples from eye tracking studies. This is from a company called Mediative, and you see how people change their eye focus behavior from the old search where you have only thin blue links until you get the universal search in 2014, when you also have images and ads and video and other kind of answers in the same page. And for example, even more complicated here, you have an eye tracking for how people look at Facebook. So you can understand better what people is doing there in this way. Very important in these studies is understanding how people will read. For example, how many results are viewed before clicking? How do users select the first relevant result? So many times it's assumed that if you click in the third result, it's because you already look at the 2 previous results. But in many people, that may be not true, because people may find the pattern right away and go directly to a result. And then dwell time is also very important. As I mentioned, how much time is spent viewing the results. Remember that the result has 3 parts: has a title, has a URL, and has an abstract or a snippet. Very important, the snippet, because the snippet today contains the words that you are searching, so you can read the context and you can evaluate the relevance without many times going to the page for that. So I will show results from different studies, from different papers. So here is how many links do users view, how many answers. And you see that that depending on where the page breaks, maybe you have a dip here. For example, after number 3, maybe it was a dip because you need to do a scroll. And of course, you have a larger dip after 10 because you need to go to the next page. So in these cases, the mean was 3 snippets. The median and the mode was 2. So 2 results. So most people click in the first 3 results in this case. This is the number of times the people selected a given rank result. So here you have, say, 11 results. You see that 11 is much less than the 10 because of this artificial break on the user interface, 10 by 10. I will talk about that. This only happens in desktop. Today doesn't happen in mobile phones. And you see that the time, for example, the time spent in the abstract is smaller and smaller when you read these things. So people read only the 3 first, the others are not read. So for example, which results are viewed before clicking, and this is to support this assumption that people read the results ranked before the one that they click. So for example, the person click in number 3, but clearly a lot of people also read the first 2, and you see that the reading behavior goes down after 3, which is the most clicked one. So typically people do not look at lower results before they click, so they click in the first one that they like. It's not like you look at 10 and decide what is the best. Maybe we do that, but most people don't do it. So that's because the people strongly believe that the ranking is good. So in some sense, there is a trust in the ranking, in the quality of the search engine. And this creates a ranking bias, which is very important because search engines have to debias this bias. So what means ranking bias? You can see it in this graph. So for example, here, for position number 1, you have almost 30% of the clicks, which is much more than 2 or 3. So this curve should be something like this. But because of two things, so there are two effects here, and we'll talk about later about this. So part of this, I would say up to here, so about 15% of this is navigational queries. So many people that instead of typing the URL, they search. And then the rest here, the other like almost, I would say 5% here, this will be the ranking bias. So this 5% is because people prefer number one because it's number one and not because it's the best one. So they're lazy and they don't go through the list. So another important thing is what kind of device they use, what is the operating system. So here are some statistics that show that most popular OS is Android, but not far from Apple iOS. Most popular smartphone, if you see only one, the brand will be Apple, followed by Samsung. And then that changes it's even more in tablets where the iPad is a dominant one. Which browser is also important because browsers have different functionality, different quality, different security. And you see here some results until 2017 that show that at that time Chrome was the dominant, then Safari, then the Android browser that's also based on Chrome, Opera, and so on. But this is changing permanently, and you can find newer statistics in the web. Which device? I already showed this one. So mainly mobile today. So it's mobile device. Now, the other way to do experiment is to do large-scale experimentation, what is called A/B testing. Basically, you do experiments with a part of the traffic of your site. So you can basically test a specific functionality or new experiences, or basically some important measure that you want to find. Here I have an example of an e-commerce site that wants to use an add coupon feature, and we need to evaluate the impact of the change. So you have two user interface, the control interface that have no changes, and the treatment will have the coupon feature, and the hypothesis is that the new feature will increase revenue, and we will do an experiment to prove that hypothesis. This is what is called A/B testing, or bucket testing. So basically you have a randomization unit that selects part of your traffic that will be part of your users. This is use-based, not exactly traffic-based. How large the experiment should be, so how much traffic you need, that depends on the impact you want to measure. So if the impact is smaller, you will need to have more traffic, or you will need to run it longer. So these are the two variables, how large and how much time. In large sites, even in hours, you can have significant results statistically. And then you need to see if the experiments scale well. So you try with 1%, 2%, 5%, 10% of traffic. And something that may be successful 1% is maybe not successful for 5% because maybe the sample was too small. Also, scaling is important. Maybe it was fast enough for 1%, but was not fast enough for 10%, and people didn't like it because it was too slow. And there's a new book, I think this already appeared. It's by Kohavi, one of the experts in this topic, Tang and Shu. It's called Experiment Guide. So let's go now to the semantics of the query. So a query can represent different information needs, and of course can be a very poor representation of that information need. Because today we don't know if people do less words because the system is very good for those queries, or people don't want to put more words. Well, the truth is that it's a vicious cycle, because both things are true. So there's an incentive to put less queries if the system works, and also there's a laziness of people to put more queries. So there's interaction, of course, and this is very important as a feedback of success. For example, even when there are no clicks, a query can be successful. For example, if someone reads what is searching in the snippet, that was successful, and even that can be measured. So users cannot change the ranking, but they can change results through the interaction. And there was a question in the previous part about how people can interact better with search engines. So important things in the context. So previous queries that are the same, previous queries that are similar, query sessions including the same query. So we can do some kind of correlative filtering using information from other users to improve the ranking of the current user. Even the query history for individuals could be used for caching. So if someone asks the same query every day, well, maybe we can have that ready. And then we need to characterize web queries first. So before trying to guess the intent or predict it, we need to characterize them. So there are many ways to characterize queries. For example, I already have shown some of them. For example, things like how many times this query appears, how many terms this query has, what is the length of the query, either in words or in characters, and so on. So these were the first studies. Just we will quickly show just the first things that were done, because today this is very easy to do. So for example, initially the mean length of the queries were 2.8. Now we're closer to 2. So this incentive to do less queries because the system works is I guess, working. For example, here is a full graph of a number of words per query. You see that the mode is in number 3, and the average will be between 2 and 3. And of course, very few people ask more than 7 queries. Many people don't know that, for example, in some search engines, if you use more than 7 queries, also that's not taken into account because it's more difficult for the search engine to answer queries with many terms. So basically, I guess they find that experimentally, and that doesn't work. You have to choose what are the best 7 if you want to use 7 or more. Something very important with caching, and I talk about answer caching. Here I have a graph of the same distribution, but the red is the original query stream, and the blue is the query stream that arrives to the search engine, because all the other queries are answered by the cache. So you see that most one-term queries are answered by the cache, some two-term queries are answered by the cache, and so on. So when that happens, then the mode of the queries, for example, goes from 2 on the original stream to 3 on the stream that really reaches the search part. So this is the real stream that the search engine sees. The other one is handled by the cache. Now, this ranking bias and these lengths of queries and all that depends on the device. So here there are different statistics. For example, CTR for one-term queries, you see that one word has the largest CTR. Why? These are the navigational queries. So people is clicking on number 1 because that's a site they want to visit. But if you see for the other results, you have the opposite graph. So the click-through rate increases when the number of words for the query increases. So basically, more words, a better query, then most probably that you will click. Now, if you see other device, for example, here, this is a different device. You see that you see the same behavior everywhere. Maybe this is a tablet or the mobile device where people is not so, they don't browse so much, so you don't have this navigational search behavior. I already showed this about voice, so we'll skip it. So basically, voice queries have longer queries. This is an interesting statistic. There are not too many statistics available for voice, but this is in Google. When they started in 2015 and 2016, you see that most queries were with 2 words, and then with 3, then with 1, then with 4, and then with 5, and so on. Now, very important, the query frequency distribution is a power law. So I I guess you have heard about the long tail. So the queries have a very, very long tail. So in desktop, about 50% of the queries are unique, so appear a single time. And also in mobile, about 30% of the queries are unique. So people are doing different things. Now, there's a very important paper that we published in Yahoo Labs in 2010 called Anatomy of the Long Tail of Queries, Ordinary People with Extraordinary Taste. And this is basically saying that it's not that there are two different kinds of people, one that does simple queries and one that does complex queries. We are both. So part of the time we're doing normal queries, and other part of the time we're doing very special queries that depends on our interest, needs, emergencies, and so on. So very important, 50% of the queries are unique in desktop, but only 5% of the terms are unique. What that means that people is using the same terms to do different queries. And this is very important because have some implications in caching. So that means that caching answers will get at the best will be 50%, while caching the index will be maybe 95% success because there are less unique terms. So here is the real example of distribution. So when you put in a log-log graph this power law, you get this almost perfect line. And the line is the slope of the line is basically the negative exponent of the power law. But this line breaks down at the end. For example, here, if you see at the end, here you have basically it's a line, it's a horizontal line, because here you have the unique queries. So all these queries appear only a single time, but the rest is quite good because follows the power law except at the end. So at the end or the beginning, like for 1, 2, or 3, basically we don't have the same line that here should be like that. Now here we have different samples of the same query log, and you see that even if you use the right sampling algorithm, so this is using the standard sampling algorithm for a skew distribution. So you weight the sampling algorithm. If you sample too small, you get the wrong distribution. So you need to be very careful when sampling queries, because you may see at the end something that is not real. So this may not be real. So you see that here you get a very long tail and you don't get the same distribution. So I have a paper on how to sample this correctly if you want to consider also the long tail. So here on the left, we have a mobile example, and you see that the mobile is less biased. So here is what I was mentioning, that this tail is shorter. So before it's like 50%, here it's like 30%. And in this statistic here, you see, and this is the paper I mentioned that I explained how to do stratified sampling to do better sampling. You see a very nice relation between different languages. So these are different languages. So they follow, doesn't matter the language, the distributions are very similar, except when, for example, here, these are 2 Oriental languages, you have other behaviors. Now, very important, this is another graph from previous research, which exemplifies something that is very relevant, is that if we put all the terms in the index in a distribution, you get this red line. So this red line is the distribution of terms in the web. So this will be the web, the red line. However, if we put the same terms with using the same order of the content in the queries, you get the green dots. And now you can see that both things are normalized. So basically the fraction of documents. So for example, this means that 1% of the documents have this red word. And if we look to the green dot, let's say these are the green dot in this vertical, then that means that this word is much less frequent in the queries than in the text. For example, here, there are two terms that are much more frequent in the document, sorry, in the query than in the documents. Probably one of these here, I don't know if you can see them, but there are more here, more dots here. For example, in one of these dots is the word free. Many people look for free things that doesn't exist. So of course, it's more popular in the queries than in the text. So the correlation is very low. The correlation is about 0.2 between the term distribution in the queries and the term distribution in the content. This is very important because that means that people is not searching what people is writing. So for experts, that means that experts should write about things they know. So if you want to see the correlation here, it's more clear what happens. So instead of having a line here, that will be, if you have a line, we basically will be, sorry. I want to write to show that here you have a line. This will be the same distribution between content and queries, but you see that it's completely different, and there are fewer here. So there are fewer words that are more frequent in the queries, but there are many, many more that are less frequent in the queries. So these are more specific words. These are all the stop words. Almost everything is here. So search clicks is another power law. So here you see another line. If you put a log graph, the number of clicks versus the number of queries. And you see here, if you go to the long tail, you see that also you have, because of the long tail of queries here, you get a long tail of a number of clicks here. So maybe it's this, some of these clicks are made by programs and not by people. And again, if you do the query click frequency, you get something similar to the query terms and document terms. So it's not a perfect correlation. Page click frequency, another power law, so very similar to, so sorry, this is the same graph. I just realized that it's repeated. So now, another interesting thing is that if you knew which pages to index, with a very few number of pages, you could cover most queries. So this is some work we did 5 years ago, and we showed that, for example, with 0.7% of the index, you can cover 25% of the queries. So with 1% of the index, you can cover 30% of the queries. So if you knew what to index, your index could be much more smaller, but of course, you need to have the whole index to decide what is the optimal point. Another thing that I have studied a lot is query sessions and missions. So query session is what you do in a session, but a mission will be the logical task that you're doing inside the session, because you may be switching between missions in the same session, and you can continue a mission in different sessions. So you need to distinguish time-based sessions that are more like physical sessions to logical sessions, which are these missions. And then something very important is to detect, and here is also using machine learning, what are the query session boundaries. At the beginning, people use like half an hour, but of course, that depends on every person. And even sometimes the session continues after a small break. So logical sessions are an interesting research problem to predict. Here is some analysis I did in the past, but here is something that related to the advanced search question. So this is one way to understand search engines. So you have different states, and then you have the probability that you are in that state. For example, here you see that in the middle, you have the results page. Here in the middle is where people is most of the time. So it's in the results. Almost 60% of the time you're here. And here we have only the transitions to another state if the transition is more than 1% of the time. So you see that if you are reading results, 62% of the time you see another result. And with these two numbers, you can compute what is the average number of pages you see when you search. So with these two numbers, you already can approximate that. This is people clicking and so on. Now, advanced search is interesting because if you see advanced search, there is no arrow coming from other states. So that means that advanced search is used less than 1% in all the other states, particularly in the home page and in the results page. So basically, if you see here also more clear, 1% of the time people send advanced search, and that 1% comes from all the states. So there's no place where at least 1% of the time they go here. And what people do in advanced search is interesting. 24% click again in advanced search, maybe because they saw that they were to the wrong place, maybe too complex. 22% goes back to the home page. So they didn't understood the advanced search. Only 8% go to refine this. Other people went to browsing, so didn't understood it. And only 27% really went to the results page. So this is an indication that only less than 0.3% of the people really use advanced search. But as I said before, you need to have it, because if you're a serious engine, you need to have advanced search, even if no one uses that. Okay, so the typical session up to now is like you have two queries of 2 words looking each time to at most 2 pages and doing 2 clicks per page. So it's almost like a pure binary search. And then the query intention problem is guess what I want. This is the problem. So with not too much information, we have to imagine what you want. Now, the good news is that mobile devices have more context. So they have location, speed, direction. So it's much easier in a mobile device to detect the intention than in a desktop. So this is the next part of semantic search. Guess the intent. So when web search was started to be really popular, Andre Brother did the first taxonomy of intents. And I already mentioned this. So navigational, informational, and transactional. So to browse, to search for information. And the last one is to get something from the web. For example, buy a ticket, reserve something, download something. You are not searching for information. You want to achieve something that is mediated through the web. And this taxonomy has been really influential in the developing of query analytics. In 2004, Roux and Levinson refined this. They proposed navigational, informational, and resource. And then they do subclasses here, informational. And here are some examples of these classes. I will not go into detail of this. You can go and look at the paper. But for example, one important subclass is the list class, which is called hub page. And this is one of the key things in authority. So you have seen the work of Kleinberg that was done at the same type of page rank. Hub pages are pages with good links. So it's not good content, good links. Here you have a page with resources, so the download. So many times you want to download something. And here you have that you're looking for a home page, the navigational queries. Now, how we can classify queries? Well, we have to use just the queries, but we can have other sources of data that can help. For example, here there are 2 that are interesting. you can use the anchor text distribution of the words in the queries. So basically, anchor text is very similar to queries. So you can use that to help. Also, you can use past click behavior, very important. Almost everything in search engines happen now through clicks. But still, we have ambiguity, and how we solve that is the key part. So the first thing that you want to predict is the topic. And as I said before, we have topic, genre. So the same thing that you want to predict in documents, you want to do it in queries. The main problem is that the document has thousands of words. Queries have only 2 and 3 words. So the problem is much harder. So I have done research on this in the past, and here's an example where we did a semi-manual classification. So we did we used clustering to do very fast labeling by labeling clusters instead of labeling single documents. And then we used the Open Directory project categories, and then we did an ML prediction. And here you have the different categories of that directory. This is already a problem because the directory mixes topics with genres. So for example, news is a genre, reference is another genre. And then it's not a clean taxonomy. And here is the number of predicted queries that are informational, not informational, and ambiguous. And you see that, for example, news, you can predict the topic very well, and it's about informational, and these are sorted by informational. And you see that there are some classes that have a lot of ambiguous queries, for example, various. Various means that more than one taxonomy is matched here, and others. Others means no class in this taxonomy is matched by the query. So very important, less context, more ambiguity. So in some sense, queries are like news titles. I don't have it here, but in some of my talks, I use a famous title from India, which was something like a spell resolve or something like that. And if you look at the title, you don't know what kind of spell it's talking about. But if you read the text, you realize that it's talking about a Harry Potter movie. But from the title, it was not possible to understand what they were saying. This is a graph of ambiguity in queries. So you see that the number of meaning per queries increases if you have more terms, and the maximum is a number in 4 terms. But then if you add more terms, you start to disambiguate, and then the number of meanings start to decrease. So this is a trade-off between number of terms and ambiguity. So if you want to see the precision and recall of the answer when you do this query intention, so if we already have if it's information or not, you get something like this, and you get what you expect. If you have information, you get higher precision and recall. No information, and you get lower precision and recall. And ambiguous is even worse. You get lower precision and recall because it's ambiguous. We also look at how these different topics were in the precision recall graph, and you see that, for example, for games, you get a very high precision but low recall, because games is a concept that is a human concept, so it's not very easy to grasp by the search engine. So here is an example where you need semantics to do better in games. And for example, adult queries have higher recall but lower precision. And you see that there's some kind of pattern between the different topics and the recall precision graph. So more recently, there has been work on trying to find topics in mobile queries. And here are some examples of from 2015. And you see that most queries are related to entertainment, trivia, local, shopping, and so on, travel. So that some people do things only on mobile and other things in desktop. Local intent versus click-through rate. So remember, this is click-through rate. So the fraction of time the click is, the link is clicked. And here you see the difference between desktop. Desktop is here and mobile here. You see that location is much more important in mobile. So here, this is for location. So more than 20% in mobile, less than 20% in desktop for the first result. Entities in queries. I already mentioned this. This is very important. This is from a paper from Yahoo Labs. You see that 40% of the queries have an entity, which is very high. So people is looking for entities, and that's why entities are so relevant. This is another paper about entities. This is from Bing. The other previous one was for Yahoo. So you see again here, they find that 29% of the queries have an entity, or an entity plus a refiner. So if you add these two, here you have already 43%, and if you add categories, you have 53, and you have a pure category, you have 57. So 57% of the queries have some kind of entity. And this graph on the right is which type of entities they find. So mainly creative work, organization, product, person, event, and others. This is our own work when I was at the intent. So these are the percentage of times that experts were used. So here you have the 50% line. So you see that about 40% of the time we were able to trigger a semantic answer. For example, the most typical was a business. So you see business is like 20% of the time was a business kind of query. For example, information about the company. And then you have weather. It's interesting that about 4% of the people is always asking about the weather. And here also you have images, which is a bit more than weather. And here you see when we didn't have an expert for image, and suddenly we started to have an expert for image, and then we were able to answer more semantic searches. Related things are, I am sure you know this, Google Trends, so I will not go into details. We did something similar at Yahoo for 4 years. My team did this and had more information than Google Trends. For example, had if this query was more popular for gender, for males or females. So in this case, the query is Angelina Jolie. That's why you have more males asking the query. Also, you have from where in the US people is asking this query. And also you have the session. Here below you have the session. For example, the previous query, for example, was Bon Jovi and or Brad Pitt, and the next query for I guess for Brad Pitt was Angelina Jolie. Now, if you can classify topics, then you can try to map queries to categories, and this is work we did to map queries to categories, and this was to count how popular was every category. And here, the size of the category is the popularity of it. So you see that in arts, the most common thing was music and then movies, and in music, the most common thing was bands and so on. But for example, here you can read maybe, but here it says organizations. So no one was interested in organizations in arts. So it's interesting because you see what people is really looking for. So if you can do this, you can do the opposite. So let's cluster the queries and see how they look. Well, they look like this. For example, here you see that there are many queries about free things. And of course, many of those don't exist, but this is a very important category in queries are queries that are looking for a free thing. Now, how we can capture semantics from the behavior to tie to what we were saying before. So let's say you have 4 queries here, queries Q1 to Q4. And let's say that people clicked in this page P1 for one, these are different people. So they click for the second query and click also for the third query. And Q4 click P2. So what relations we can find that are semantic here? So the first relation, is common words. So maybe 2 queries are related if they share a same term. So this is a valid semantic relation, but it's not always right. The next relation is a common session. So Q3 and Q4 are related because they were typed by the same user in the same session. So probably this is the same topic. The next one is common click, and this is very powerful. So basically, Q2 and Q3 are related because they click in the same page. The next one is a link relation. Maybe Q4 and Q2 are related because a click of Q4 links to a page clicked by Q2. And finally, we can have the same relation, but not based on links, but based on common terms. So basically, there's a high similarity between the content of P2 and content of P1. So all these things are possible semantic clues that are language independent. This is very important because this will solve partially the question about what happens if we have no knowledge base and no natural language processing for that language. So here is an analysis on 3 attributes of these relations. So like strength, how good it is, sparsity, how many we have, and noise, how many problems we have. And here basically it's my qualitative evaluation. And here you have noise. So polysemy is a noise in word relations. Physical session is noise on the logical sessions. Click spam is noise on clicks. Link spam is noise on links. And term spam is noise on terms. But see here, strength is very high for clicks. This is the key one that I will show in the next examples. So let me give you an example. So these are real queries. These were from the Yahoo search engine. These are queries about Shakespeare. And this is the word relation. So this edge exists here because there are 2 common words. And you see that this person didn't know how to write Shakespeare. But because of William, we have the connection to the right spelling of Shakespeare. So for example, this graph could be used for spelling correction. Now, these are the relations between terms. What happens now if we go to a different relation? And here is the session relation. So these are how people did queries in the same session. So you see that, for example, and for technical reasons, the arrows are the opposite. So really, the real order is that the person was looking for calcite, maybe doing homework, then went to write Shakespeare, wrong spelling, then probably the search engine corrected it. So Shakespeare, the right spelling. Maybe the answers were not so good. So William Shakespeare, still not good enough because the person was looking for the biography of William Shakespeare, but also doesn't want to work too much. So it's looking for the short biography of William Shakespeare. So you see here also minimal effort at work, like a student solving homework about William Shakespeare. Now, what happens if we see the click relation? So very, very different. And here you see that they have a cluster of questions with William Shakespeare. And this is why this is so important, because that means that all these pages are related by a single topic. And then this connection are really semantically very strong. So this is our assumption that the user feedback is a positive feedback when you are looking at clicks. Here's some examples. So these are clusters of the click graph for travel. So you see here you have a cluster for Italy. Here you have things about other trips. Here you have a cluster for Barcelona. Here a cluster for Paris. So basically, similar queries are clustered because of they are going to similar pages. But we don't need to find those similar pages. We just look at the clicks. So with this, we can find query facets. This is the powerful thing about clicks, because now we are getting some semantics for any language. For example, this is a facet for the term lonely. So lonely has two facets. One is Lonely Planet, so it's about travel, and one is about lyrics in music. So we can immediately automatically, without understanding what are these things, a person can say, okay, this is travel. You just need to label the clusters, travel, music, and you are done. You can find, for example, also different brands. For example, if you put here hard disk, you will get different clusters for every brand. So you can build a query-based taxonomy. I call it a taxonomy because it's not a taxonomy. So it's a taxonomy coming from people, so it's a taxonomy. And here you see some interesting clusters. For example, this one here is about Wikipedia. And you see that basically free encyclopedia is a synonym of Wikipedia. Because when people look for free encyclopedia, they click in Wikipedia. Even you get all the misspellings. So you can handle also spelling correction from this cluster. Here is a cluster about Firefox. You see people that doesn't know how to write Firefox, it says Foxfire. Some people know it's Mozilla. Some people put a space in between, but basically all these queries are about Firefox. Here it's about Yahoo, and you see that there are some that are misspelled. So we can build this, and then we can say, if we can use a set-based approach, so we can say that if all people click in the same pages for two different queries, these queries are synonyms. So for example, this red here means that all the people that look for JR click in the same pages that people that look for JR music world. So these two are the same. For example, here, AJ is the same as Jeeps, although J should be G. So even you find spellings. For example, here, TFCU is an acronym for Teachers Federal Credit Union, but all the people that ask for these two queries, they get the same, they look to the same pages. So basically, the red are synonyms. Now, what are the greens? The green means that they click in a subset of pages. So basically, let's say we look at area code. So area code, so all the people that look for area code clicks on these pages. So this is a set of pages. But the people that click for area code lookup, they click in a subset of these pages. So we will say that this query is more specific because they click in a subset. And these are the green edges. And then if they click in a subset that is intersecting the subset, like this case, we will say that this is a black edge. So there is some relation, but it's not contained. So these are the other edges here. Now, after we have this, we can build a dictionary, right? We can build this thesaurus with three relations: synonym, more specific, related. And then we can try to evaluate that. We can try to evaluate that, and we did that using the Open Directory project. So this is the number of answers that we look in the category, so from up to 5, and this is the similarity that we get from the directory. And you see that synonyms, you get 70% accuracy if you look at 5 answers. More specific things, you get more than 60%. Related things, you get almost 20%. And if you do random, so basically if you do random similarity, you will get less than 10%. So this is really 10 times more. So it's very significant, this kind of semantic relation. So this is the way to capture semantics from behavior, and this is language independent, and we can build this. You can build like a thesaurus just based on clicks. So to end, I will talk about a little bit about privacy. So in 2006, American Online decided to publish an anonymous query log So every user was a number, integer number. But then two journalists from New York Times, looking at the query that this person used, this person 4 million something, was able to identify this person. So this was the first de-identification done in internet. Now, New York Times have done many more using data from games. For example, there was a very interesting set of 4 articles in last December about privacy in the web. Even they follow Trump because of security people playing games in their mobile phone while they wait. So they were able to identify this woman and went to their home, and they asked her if these queries were hers. And she said yes. You can always say no, but she said yes. And then they asked her if she wouldn't mind to be in the newspaper, and she said no, I will be nice. And she went to the first page of New York Times. So she was a celebrity. She was so nice that didn't sue American Online because this was something illegal to give data away to identify people. But show that was easier than we thought to identify people from query logs. And then because of that, we decided to do some research on it and to see how difficult it was to identify things from queries. And the truth is, it was not that difficult. So for example, here is a sequence of papers where using machine learning, you can guess the gender from very few queries, 84% accuracy. You can guess the age plus minus 10, so a range of age, 79%. And even you can predict the 3 first digits of the zip code with 35%. So basically, this is a profiling tool. If you want, going back to Shalini's query, that how you can profile, even with queries, you can profile quite well, especially gender and age. So if some person here has never searched her or his name in the web, please put it in the chat, because I would like to talk to that person. But most people search for their name. And if you search for their name, you are giving away your identity. So you are already helping, if you are not logging, the identity. So, and this is more than you think. So partial name is 9%, complete name is 1%. So this is the level of vanity in the web. So next time that you feel the urge to search for your name, ask a friend to search your name, and then at least you mix the data. Otherwise, you're giving away your identity. So I think we have, I don't know, we have some time for questions, Shalini?
Yes, we do have, we are more short, but still I think we can take some questions if there are any. There was a question that was raised in the question and answer box by A. Pandya Raj. Are you there, Pandya Raj? How can queries be classified was the question. Pandya Raj?
Well, I can answer the question.
Okay.
So maybe I don't know when he asked the question, but for example, using these ideas that I talked at the end, the query mining part, using clicks, you can classify queries very easily. Because, for example, if you have a very good document classifier, then if you have labels in documents, you can use those. You can see the labels of documents clicked by those queries, and then you can classify the query with the same label. So if the query is multi-topic, you will get many topics, but if it's single topic, you will get just one. And this is what you can do, and this is what is done. So very easily you can infer query topics from document topics.
Has anyone raised their hand?
Yeah, there is a question from Mohammed Minaj.
Minas, ask your question, please.
Context of my question. In the first session, you...
Can you speak
Minas,
louder, because I don't hear you?
We can't hear you, Minhas.
I'm audible now?
Now better.
Now it's better.
Okay. Professor, just to set the context of my question, in the first session, you explained a use case, Yahoo's use case, wherein you could predict the next app that is going to be open. And in this session, when you were talking about understanding the context of the query, the intent of the query, you also mentioned about collaborative filtering. So I was just trying to connect this two and was wondering, can we create a system through which we can predict the next query that is going to be entered by the user? And for this, as a research problem, employing collaborative filtering, do you think will be the right approach? And if so, should it be based on the user filtering or should it be based on the content filtering?
That's a good question. I don't know if this has been done. Probably, maybe. I never heard about predicting the next query, but it's an interesting question. So, so I would say that I would say will be more on the user filtering side. Although my guess, if you want to do it well, you need to use both. In the example I showed in the first part about predicting the next app, the most important thing that we learned is that was not about the position, was not about the user, was not about the time, was about everything together. So this is the power of deep learning, that you can understand the whole context. And I will say that for the next query, you need to do the same. So you need to use all possible sources. So the main advantage of using collaborative filtering is that you increase the size of the data, because if you use only queries that for one single user, you don't have too many. So you cannot use deep learning. But if you use like all the people that is trying to do the same intention as you, this is a huge number of users, so it's much more data, and then you can use deep learning techniques. So collaborative filtering for me mainly breaks the barrier of also helps on the privacy part, because you don't need to know the user, you just need to know the intention. So you don't need to know the person. So that's another advantage. So you don't care about what's the queries of the user, you care about what are the similar queries to yours, independent if it's a cookie or an IP address or whatever. And also collaborative filtering also solves this filter bubble problem. I don't know if you know about filter bubbles, but basically, if I only use data that I have for Shalini, I will never be able to predict to suggest something that she doesn't know, but if she knew it, she would like it. So you need to break the filter bubble, and collaborative filtering breaks the filter bubble. That's another advantage of collaborative filtering.
Thank you, Professor.
Madam, you need to unmute yourself, please.
There is one question from Sangeeta Narang. She's asked whether this, the query privacy issue, which is more dangerous, the CCTV watching us all the time, or Google or somebody watching us all the time?
I think it depends for what. So as usual, there's no single answer. It depends on the application. Like, I would say that facial recognition is, I would say there's more discrimination there. So it's a discrimination angle.
Okay.
But in the case of queries, you know much more about the person. So you know everything, because queries have semantics, and this is the thing. So it's a face doesn't say what people are thinking. Queries say what people are thinking.
Okay, thank you.
But for example, for I guess for surveillance issues, I will worry more about facial recognition. For profiling issues, I will worry more about search engines.
Okay. I have a question, if others are not having a question. See, this query auto completion, that feature is now, common. So my question is, doesn't it standardize the queries to a certain extent? And what has been its impact?
Yeah, this is similar to the thing that why people use the terms, because of query auto completion, or we get back to the same thing. Yeah, so this adds a bias for certainly. So adds a bias to standardize the query. So in some sense, you kill some diversity. Maybe a person would use another word, but the completion is faster. So I think that is not good for search engines to use too much of a query to completion. The best will be that
Yes,
people write the query completely.
Huh?
But because it has become a standard, that's very hard to do. So I agree
Yes,
with
yes,
you. So for example, as in clicks, in query to completion, also you need to debias clicks, because people will click more on the most common ones, but that doesn't mean that these are the best, because otherwise also the query auto completion will become standardized and will be boring. We will have only typical things, and sometimes you don't want that. So this is the problem. So you're helping people by the time you are adding biases to both the people and the system.
I have one more question. You mentioned about the long tail of queries, etc. Usually, digital marketing people use that long tail for marketing purposes. But here, I mean, from a search point of view, it's kind of different, right? So the digital marketing people use the words in the long tail because it is not as expensive as this. So my question is about how do you balance the two? So there is a market for the long tail of infrequently used words, right? And that tilts to a certain extent, according to me, because when digital marketeer starts using the words in the long tail, and then that kind of moves from the long tail to the main, right?
Right.
Does that happen or does not happen?
No, that happens. But for example, in experiments we have done, if you take any segment of time, let's say you take 1 week, and you compute the correlation of that week with the next week, and you keep doing this for a year, we found that the correlation was 99.5% all the time. So there is a background of queries which are very stable. But when you see trends, you see just the outliers. So when you see the things that are not always on the head or not always on the tail. So when you see the changes are outliers. So I believe that there are things that go from the tail to the head, and sometimes they come back. Let's say something that it becomes the head because of the news. For example, some presidents, I surely will go to the tail in the next future. So you have this kind of behavior that the terms are being moved from one place to another. But I would say that marketing helps to move some of them to the head forever, like brands, like products. Apple has done that very well. So yes, so that's happened. But what I'm saying, because of the correlation, if you compare that to the huge number of queries that you have, it's almost nothing. So it happens, but happens very little.
Okay, thank you. Who else has a question? Are there any more questions?
So I will say, let me thank Somnath and Shashi because of the comments to my talk.
Can I ask one more question, please?
Yes, for me, it's okay.
Ma'am, it's okay.
Minas, go ahead
Yes,
and ask your question.
sure.
I guess it will be the last one because I have a meeting in 10 minutes.
Okay, this is the last question. Okay, then.
Yes.
Sure. Sir, with finer granularity of data, we'll be able to perform better query analytics. But with data compliance like GDPR taking center stage, it may be challenging to store the data and also to access the data. So as a research problem, if you could kindly actually help me understand, are there any data sets, just like we have SemEval, etc., for validating relation extraction, for performing this kind of search analytics? Are there any data sets that can be used?
There are some, not too many. For example, the AOL query log, they took it away one day after the event, but it's available in many places because people copy it and put it back. So it's kind of illegally available, but people use it to do this. There are some small queries data sets that have been shared by Microsoft and Yahoo. They are available too in some places. In some cases, it's only for academic use and you need to sign an agreement. You can always have your own search engine or your own proxy, I mentioned, to get data like this. And And even if you have more data, the problem of with GDPR, what I imagine in the future is that in many cases, if you transform this data to say word embeddings and language independent, really you don't need to know what exactly the word you are searching and who is doing it. You need to know what semantics you have. So in the future, I expect to have like all this data using word embeddings, which is much more anonymous, but still you have semantics because of the word embeddings. Of course, it's not pure semantics, it's pseudo semantic, but it's semantic that works quite well if you see things like BERT or GPT-3 and so on.
Okay. Thank you, Professor.
Okay, thank you so much, Ricardo. Now this is a formal vote of thanks to you. I'm sure you have had a busy day and you are somewhere in, Barcelona, right? You are in Barcelona.
Yes, I have to give a talk later today also in Cyprus.
Yeah, and you have a meeting to attend to, so I won't hold you longer. So on behalf of all the organizers, particularly Informatics India, so I thank you very much, and let me also introduce Mr. Satyanarayana, who has already asked a question, who is the founder, chairman, and managing director of Informatics India. And that is the company that is actually behind this LTC conference. And then we also have committee members here, Dr. Anand Bhairappa and Dr. Meera. So I don't think they're visible. Anyway, I wanted to introduce them to you. And of course, Devendra Thakur from Informatics, who is the person behind all the arrangements here, particularly the platform and all that. So he's here. And I see Meera, so that is Dr. Meera. So she's one of the members of the committee. Anand, are you there? Somewhere, anyway. So thank you so much. And we should also I should not forget to thank ACM, because it's part of the ACM Distinguished Speaker Series. So thank ACM for that. And of course, but not the least, actually, our participants who are still there till the end. So thank you so much for attending, and thank you so much for your questions. With this, I think we come to an end. So we will be in touch, Rick, okay? So personally, I really thank you, because I have bugged you enough regarding this and asking for changes in time and all that. Thank you so much.
Okay, thank you. Bye-bye.
Bye.